Good morning, all of you. In this session, we are going to start with 10th Standard Chemistry and Physics, Unit number 7, Classification of Elements, the Periodic Table. So here, series number 8 is going to discuss about the concepts which are relevant with the periodic properties, which are going to be discussed in the various groups as well as in the periods. What could be the repetition of the properties, how there is a gradual increase and the change in the properties are possible in the modern periodic table. Those topics are going to be discussed in this session. In addition to this, we already completed about unit number 1 to unit number 6, entire detailed discussion about these 10th standard chemistry and physics. All these are available on the channel called World of Competitive Chemistry. Let us discuss about today's concept, periodic properties of the elements in the modern periodic table. So, modern periodic table purely based on the atomic number of protons which are present in the central nucleus. In addition to that, we can alternately define as physical and chemical properties of the elements are electronic configuration, in particular outer shell configuration. So this is the definition in accordance with the modern periodic table. Even though earlier so many kind of perceptions are provided, but it is a widely accepted kind of modern periodic table which purely based on this kind of categorization. Modern periodic table used to organize all the well-known elements, and the elements are arranged in the table increasing their atomic number. Modern periodic table, each element is represented by a chemical symbol. When you go with hydrogen, it is H. Helium with the He is there. Right. So in that manner, chemical symbol is used to describe that entire periodic table and all the elements, because it is very difficult to accommodate the entire name of the compound. In order to simplify, the long form of periodic table is represented with a single digit called hydrogen with H, helium with H. In that manner, simplified chemical symbols are denoted for them. Right. So here vertical columns are denoted as groups and horizontal rows are denoted as the periods in this modern periodic table. And this is about the simple representation of all the repetition of properties in the periodic table. Electron shells, when we move on from top to bottom, this is the entire periodic table and the properties representation with respect to the new periodic table, where in this direction, if you are going from top to bottom, what happens in the group, how the properties are varied can be represented. From left to right in the period, how the properties are variated can be represented. So this is the way of representation of periodic table. So when we are moving from top to bottom, what happens? The shell number gradually increases. So if for each shell, principal quantum number will be added, so that here when we are ascending in a group, what happens? Its shell number will be rapidly raised. But when we consider a period from left to right hand side, each electron will be added to the same principal quantum number. That's the reason why here the shell number will not be varied. It remains same from one element to another. So, and the next is about valency electrons. So when we move on to in a group from top to bottom, valency electrons remain same. That is purely because of, based on the valency electron similarity only, all the elements are categorized into a single group. Because of the similarity in the valency electron, their properties also resembled. That's the reason why when you consider valency electrons in a group, all are possessing same kind of valency electrons. If you consider first group elements including hydrogen, lithium, and followed by sodium, potassium, rubidium, cesium, and francium, all are consisting only one electron in its outermost shell. That's the reason why valency electron count remains same in the group. When we move from left to right hand side, what happens? Their valency electron count will be gradually increases. So let us consider a simplest group called the first period. Hydrogen with 1s1 electronic configuration, move on to helium 1s2. That means that there is a gradual increase in the number of valency electrons are possible, move on from left hand to right hand side in a period. And next is about electronegativity. Electronegativity is nothing but tendency to gain the electron is called electronegativity. So as we are descending, what happens? Electropositivity will be raised so that electronegativity will be the reciprocal, that is gradually decreases from top to bottom of any group. So let us consider first group again. Lithium is what we can say more electronegative, and as we are descending, and cesium is more electro. In the entire periodic table, you can consider cesium is the most electropositive element, and in that manner, electronegativity will be gradually decreases from top to bottom. And move on to period. From left to right hand side, electronegativity values are gradually increasing, right? So here, let us consider the second group elements which are started with the lithium, lithium followed by beryllium, beryllium followed by boron, boron, carbon, nitrogen, oxygen, fluorine, and followed by neon will be there. So this is a second period where 8 elements are incorporated here. As we are moving from left to right hand side, what happens? Electrons will be added to same main shell. That's the reason why nuclear charges gradually increases. Because of that reason, size will be concised and more electronegative atom will become. That consequently results, fluorine is the most electronegative element in the entire periodic table. So that's the reason why from left to right hand side, as we are descending, what happens? Electronegativity values are gradually increases. And move on to another property called ionization energy. Ionization energy denotes the amount of energy required to remove the electron from the gaseous atom is called ionization enthalpy or ionization energy. So as we are descending down the group, what happens? Size of the atom gradually increases. It's very convenient to remove the electron, so that ionization energy values are gradually decreases as we are descending down the group. But moving from left to right hand side, ionization energy values are gradually increases, right? So this is the pattern of ionization energy in group as well as in the period. Move on to electron affinity values. Electron affinity is nothing but amount of energy released when electron added to the gaseous atom. So when you take chlorine, for example, because it is the most highest electron affinity element in the entire periodic table is called chlorine. So that's the reason why I'm taking the example chlorine. When electron is added, how extent the energy released in the gaseous state is called electron affinity. So when we are moving from top to bottom, electron affinity values gradually decreases. Rather, electron releasing tendency will be raised. Move on from left to right hand side in the period, electron affinity values are gradually increases, right? So electron affinity values gradually increases. And next is about metallic nature, non-metallic nature. Top to bottom, non-metallic nature gradually decreases because in any group, as we are descending, metallic nature gradually increases. At the bottommost element, almost any group you can consider, in all the groups, the bottommost element will be most metallic in nature compared to topmost, right? So that's the reason why metallic nature gradually increases as we are descending down the group. And from left to right hand side, that means across the period, what happens? Metallic nature gradually decreases. And move on from S block to D block, D block to P block, gradually non-metallic nature increases. Most of the P block elements are metalloids and non-metals. S block elements purely metals. D block elements are transition metals. A block elements are inner transition metals. That's the reason why around 80% of the elements in the periodic table are regarded as metals only. So this is the entire description about the periodic properties of all the elements which are present in the modern periodic table. In continuation to that, the atoms and the elements in the group possess similar electronic configuration. As we discussed, so in any group, outermost electron count will remain same. That's the reason why their valency electron configurations are similar. Consequently, physical and chemical properties also similar. You can predict, you can apply the similar kind of physical and chemical properties, the elements which are grouped in the same group, right? Conversely, when you move on from, when you are considering a period left to right hand side, what happens? properties variation will be observed because electronic configuration gradually increasing, right? So that's the reason why in a group gradually valency electron remains constant. That's why chemical properties are resembled in a group, right? So similarly, across the table, left to right hand side in a period, increasing the atomic number by 1 unit. I'm taking again the first period as an example. Hydrogen to helium. Hydrogen atomic number is 1, helium is 2. That means in a period when we are ascending, what happens? Always rise in the atomic number is observed by 1 unit between any two successive elements. Therefore, electronic configuration of valency shell of any two elements in the given period is not same. Electronic configuration resemblance you can observe only in a group but not in a period. That is, yes, that's the reason why. So when we are moving from left to right hand side, electronic configuration gradually increases, so that properties also periodically varied. Periodical change in the properties are observed in a period. Due to this reason, element along the period possess different chemical properties and the regular gradation in the physical properties are observed. To understand this, we will take some properties of elements and discuss how they vary in a group as well as in the period. So these are the trends which you can clearly observe in a group as well as in the period. Atomic radius from top to bottom gradually increases. Ionization enthalpy values are increases from left to right hand side. So least ionization enthalpy values elements are found in first group elements. So this S block elements are having least ionization potential, and also electron affinity values are least for these elements. So here S block elements are mostly metals. As we are moving from left to right hand side, non-metallic property gradually increases. So when you are moving from P block to S block, metallic property gradually increases. Atomic radius will be decreased from right to left hand side. Electron affinity values are increasing from bottom to top. Electron affinity values are increasing from bottom to top. Actually, fluorine should be more electron affinity element, but being it is a smaller one, electron repulsions are observed. That's the reason why fluorine is the most electron affinity element in the entire periodic table. Ionization energy values are increasing from bottom to top because smallest the atom, greater will be the ionization enthalpy value. That's the reason why there is a increase in the ionization enthalpy is observed. So in a group. So these are the trends which you can clearly observe by taking these arrows. And we are going to discuss in particular about certain properties, how they are varied in a period as well as in the group in the new periodic table by taking certain parameters as an examples. First one, we are going to consider with the valency of the given element. Valency is regarded as valency of the element is regarded as a combining power of the element. How many bonds it able to form? Initially, this combining power purely considered with either hydrogen or oxygen. How many bonds that element able to form with hydrogen? Otherwise, how many bonds that able to form with oxygen? With respect to these standard elements, here valency is calculated. For example, if you go with chlorine, it able to form only one bond with hydrogen. That's the reason why chlorine valency is regarded as 1. Hydrogen always one valency, it able to form only one bond. When you go with oxygen, these two hydrogens are able to form 2 bonds with oxygen. That's why oxygen valency will be 2, right? So here valency of any element by taking standards of hydrogen and oxygen, their valency are used to be calculated. Chlorine able to form one bond with hydrogen. That's the reason why chlorine valency is regarded as 1 in general. But there is a range of valency up to 5. Up to 5 bonds it able to form. But with respect to hydrogen, it able to give only 1 bond. Oxygen able to give 2 bonds with any other species. When you consider water molecule, oxygen able to give 2 bonds. That's why oxygen valency is regarded as 2. So these are the various valencies of the elements ranging from atomic number 1 to atomic number 20. And this is the data collected from the platform called Brainly. Thank you for your information. Now let us see atomic number of the elements and the consequent atomic masses and their valencies of the elements. Hydrogen atomic number and atomic mass both are exactly equal. Hydrogen either gains, otherwise loses the electron. Dual property will be there for hydrogen. So that's the reason why valency is regarded as either -1 or +1. When you go with helium, being it is a noble gas element, and neither releaser nor accepting the electrons, that's the reason why its valency is given as 0. For most of the noble gas elements, their valency is regarded as 0 itself. Atomic number will be 2, and when you double this quantity, it will become 4 atomic mass. And in the similar manner, there is a regular gradation in their atomic numbers. We are considering 1 to 30 elements here. 1 to 30 elements are considered, and their consequent valencies. Valency is nothing but how many bonds it able to form. Otherwise, another version will be how many electrons lost or gained by that species. In two ways, valency of the given element can be defined. So in the given all elements here, you can find the highest oxidation state as a +7, and that is given for chlorine, and also it is given for manganese, being it is NS2 NS2 N-1D 5 electronic configuration. That's the reason why it able to lose 7 electrons. But highest oxidation state in the entire periodic table, that is assigned as +8. Osmium and ruthenium, these two are the elements which used to give +8 highest oxidation state in the entire periodic table. That is the known highest oxidation state till now. So this is about the valency of given element in terms of ability to form the bond, otherwise ability to lose or gain the electrons. Now, valency of the element with respect to hydrogen is the number of hydrogen atoms by which one atom of the element chemically combines. Here, when you consider oxygen able to bind with 2 hydrogen. That's why oxygen valency is regarded as 2. Oxygen is bivalent in nature. So here, when you go with, so here individual group elements and their valency are clearly described in this continuation form. Hydrogen having the valency only 1, it able to form only 1 bond. When you consider HF, hydrofluoric acid, it able to give single bond. But when you go with oxygen, it able to combine with 2 hydrogens, so that here bivalent oxygen is found here. And I'm taking the example sodium as first group element. Sodium being it is the alkali metal, having tendency to lose only 1 electron, able to form 1 bond, so that its valency is regarded as 1. And moreover, you can take sodium hydride. In that case also, sodium able to give 1 bond with hydrogen, 1 bond with the chlorine. So here sodium chloride is a common table salt we are using in our daily life, where only 1 bond you can observe, being it is ionic bond, what you can say transfer of electrons are possible. And next compound I'm going to consider magnesium chloride. Magnesium alkaline earth metal, where 2 electrons lost by this magnesium, and it able to form bond with the 2 chlorine atoms, so that its valency is regarded as 2. So here where you can go with the how many groups are there in the new periodic table? 1 to 18 are there. Sodium being it is the alkali metal, first group element, it is able to give only 1 bond. Magnesium is the second group element, where 2 bonds are possible, and it is said to be a bivalent. Here there is a clear comparison that what is the group number, similar valency is observed for these. Move on to boron. Third element will be boron, being it is a third, or in accordance with the new modern periodic table, it is regarded as a 13th group element, where it able to give 3 bonds around that planar mighty it will be, and the 3 chlorine atoms get combined with this one. So here trivalent, boron will be a trivalent. Carbon, 14th group element, where carbon surrounded by 4 hydrogens. That's the reason why you can say it is the kind of tetravalent. Carbon is a tetravalent in nature. I am moving to any other group, 15th element called the phosphorus. Able to find the bonds with the 5 chlorine atoms, phosphorus pentachloride it will be. Central phosphorus surrounded by 5 chlorine atoms. Here, this will be a pentagonal, right? So here, 5 bonds are possible, being it is a 15th group element. And move on to 16th group called oxygen family, where sulfur is the element. It able to give how many bonds? 1, 2, 3, 4, 5, 6. 6 bonds are possible with this. So here, 6 bonds it able to generate in its surrounding, being it is the 16th group elements, its valency can be regarded as a 6. And another element I am considering halogen element, that is iodine, which able to give 7 bonds around that in iodine heptachloride. That is called interhalogen compound. Around the iodine, 7 chlorine atoms are going to be surrounded. So which is said to be ICl7. And next is about a noble gas. Noble gas, being it is highly stable, completely filled, and more stable element which are present in the 18th group, and this is regarded as, this is whose valency is regarded as 0. Neither be lost nor be gained, because being it is a noble gas and a stable configuration, and it able to give such a kind of 0 valency, right? So it is the stable. All the elements which are present in the periodic table having strong tendency to attain the noble gas configuration, because always all the elements having strong tendency to get the stability, right? So that's the reason why this is about the comparison of various valencies of various groups when we are moving from S block to P block. All right. So here, let us go with the valency of element with respect to oxygen will be the twice the number of oxygen atoms, because always oxygen able to give a double bond nature rather than single bond. That's the reason why. How many hydrogens combined directly, you can go with its valency. How many oxygens combined, you have to double the number. For example, in H2O molecule, 2 hydrogens linked with 1 oxygen. That's the reason why here always we have to go with the doubling the number in case of oxygen binding is there. Note that the group number of the element gives the maximum valency of that element. I'm taking all these examples. All these are the simplest examples for maximum valency of those elements. Go with the phosphorus, being it is a 15th group element, 5 will be the valency. Sulfur is the 16th group element, 6 the valency. Iodine is the 17th group element, 7 the valency. So in this manner, here group number directly resembles the maximum valency of that particular group element. Right. So here, in accordance with the Roman numerals, 1 to 8th group elements are there, but 18th group elements, 18 groups are measured in accordance with the modern International Union of Pure and Applied Chemistry numbering. So there are 18 groups are present, started with 1 and ended with 18. Now, for example, I'm taking sodium as an example. Chemically combines with 1 hydrogen. Sodium, being it is monovalent, having tendency to lose 1 electron, able to form 1 bond with a hydrogen. This is regarded as a sodium hydride. Sodium hydride, where sodium valency can be taken as 1, because the ability to form bond with hydrogen will be only 1. Move on to calcium. So when you consider calcium oxide, so just now we discussed that number of bonds with hydrogen equal the valency. Number of bonds with oxygen mostly double the valency. Here, calcium with oxygen. So 1 calcium, 1 oxygen is there, but we have to double the number of bonds. So here, its valency is taken as 2 rather than 1. Because calcium, oxygen both are linked with double bond nature, here it is clearly represented. Right? Calcium oxide, Ca, double bond, O will be there. So here calcium will be bivalent. Sodium will be monovalent. So this is about the valency of given element. Now, let us move on to, in general, valency of the element with respect to hydrogen is in its traditional group number. So here, traditional group number. So if group number is 1, its valency is also 1. Sodium, being it is a first group element, sodium chloride, where how many bonds you can find here? Only 1 bond. Magnesium, being it is a second group element, how many bonds you can find? 2 bonds with the chlorines. Not only chlorine, you may go with any element. In combined state, magnesium able to give 2 bonds. That's why its valency will be 2. And move on to 13th group element, boron. So here 3 bonds present around, hence you can say its valency is 3, and in the Roman numerals you can say it is the 3rd group element. Carbon being it is the 4th group element in the Roman numerals, and its valency is 4, right? So here group number exactly equals to its valency up to this group only. So here if the element of group 5 are above up to group number 4, you can apply the same concept. Group number exactly equals to its valency. So if it is placed in group number 1, only 1 electron it will lose and 1 bond formation is possible. That is applied up to only 4th group. From the 5th group, the pattern will be different, because we have to take the valency is equal to 8 minus group number. Subtraction pattern will be followed again. 8 minus group number, for example, group number is 5. 8 minus 5, it will become 3. 8 minus group number, for example, I'm taking group number 6. 8 minus 6, it will become 2. Valency will be 2. 8 minus 7, valency will be 1. 8 minus 8, valency will be 0. In that manner, after first, second, third, fourth, there is no change. What is the group number? Same valency will be assigned. But move on to 5th group. I'm taking 5th group element, nitrogen. In ammonia formation, how many bonds it able to form, bind with the hydrogen? 3 bonds are possible. This is denoted as a pyramidal in shape, right? So here, being it is a 5th group element, 5 bonds should be present, but rather it able to give only 3 bonds. The reason is, here from the 5th group onwards, what we have to do? We have to take octet. Octet means completely filled configuration called 8 minus group number. For nitrogen, what is the group number? Group number is 5. 8 minus 5, it will become 3. So here it able to form only 3 bonds. This formula can be employed for 5th group to 8th group. Now let us consider 6th group element, sulfur. I'm taking sulfur, 6th group element. Let us apply the formula 8 minus 6. How many bonds it able to form? Only 2 bonds. H2S. Dihydrogen sulfide it will be. Rotten smell it consists of, right? So here H2S being it is a bent shape molecule, resembles water, and its valency will be only 2. Move on to 7th group element. I'm taking chlorine. 7th group element, what we have to do? 8 minus group number is 7, right? 8 minus 7, it will become only 1. That's the reason why chlorine will bind with 1 hydrogen and become monovalent. So this is the common valency, but maximum valency will be the group number itself. 7 bonds it able to form in general. And I'm going to 8th group element, taking neon, for example. So 8 minus group number will be 8, right? 8 minus 8, it will become 0. That's why neon doesn't form any bond with any species. So it will become noble gas. So in that manner, up to group number 4, one kind of criteria will be followed. Up to group number 8, 5 to 8, we have to go with new pattern, new kind of calculation of its valency, common valency it will be, right? And in general, each period starts with the valency of 1. So I'm taking second period as an example, and what could be the general trends observed in properties, how the periodical change of properties are possible, that we are discussing. In general, each period valency will be started with 1. If you consider group number 2, where lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, these are the elements which are incorporated in a group number 2, right? So here lithium valency, how many bonds lithium able to form? Only 1 bond. If you take lithium hydride, 1 bond. Lithium chloride, again 1 bond. That's the reason why any period always valency will be started with 1. For first group elements, increases up to 4. So lithium 1, beryllium 2, it is a linear molecule. Boron 3, it is the planar molecule. Carbon 4, it is the tetrahedral molecule, right? So it reaches up to 4. After reaching 4, again there is a descending in number are possible. Move on to nitrogen. what should happen? It should become 4 to 5, right? But there is a periodical trends. What is the trend here? After 4, again there is a decrease. It will become 3. Nitrogen in ammonia, it will give only 3 bonds. Later, oxygen will give only 2 bonds with water. In water, for example, with the calcium also 2 bonds, so that oxygen valency will be 2. So after 4, again there is a decrease in the valency. You can observe 3, 2. Fluorine. How many bonds fluorine able to form? Can you find anywhere? Fluorine able to give only 1 bond, HF. How many bonds are there? Only 1 bond. That's the reason why its valency is only 1. When you move on to argon or neon, what happens? Its valency is 0. Just now we saw here neon valency will be 0. In that manner, there is a regularity in the properties. 1, 2, 3, 4. Further, 3, 2, 1, 0. That a kind of what a gradual change in the properties you can observe with respect to valency, right? So I'm taking same kind of series here. Lithium, HLI, lithium hydride, it is designated, and 1 bond you can observe here. Beryllium chloride, linear, where beryllium surrounded with 2 chlorine. Boron trichloride, planar, where planarity is there, 3 bonds are surrounded with boron. Carbon tetravalent, so that 4 chlorines. I'm taking example carbon tetrachloride, where 4 bonds are present around the carbon atom. And next is about NCl3. You may take ammonia also. So when NCl3 was taken, nitrogen surrounded with only 3 bonds. So here it will be trivalent. After 4 bonds, again there is a decrease in the valency. You can clearly observe 4 to 3, 3 to 2, 2 to 1, 1 to 0. Then I'm taking one more example for oxygen. Oxygen will give 2 bonds. So here I'm taking OCl2. So here oxygen valency will be 2. Again I'm taking Cl2. So this is a halogen family. After 2, it will be 1. So that means chlorine able to give single bond, general valency. And I'm taking another example, organ. Organ will not form any bond with any species, neither lost nor gained. So here it is a 0 valency. So these are the trends you can clearly observe in a period. Now, there is a new kind of perception regarding this valency of the electron. Earlier, only purely based on the number of bonds, valency was regarded. But nowadays, trends were changed. Valency of the element generally taken as the number of valency shell electrons present in that. Oxidation number concept almost taken as a latest substitute to the valency concept of modern literature. Nowadays, how many electrons it is losing, otherwise how many electrons it is gaining, based on that electron transaction concept only nowadays this valency was discussed. I'm taking simplest example, barium sulphide. Barium will lose 2 electrons, sulfur will gain 2 electrons. That's why barium is bivalent, sulfur is also bivalent. Valency of barium is 2 and sulfur is also 2 based on their oxidation number. So this is a new concept. So new version of thinking regarding valency of the electron. Calcium oxide, calcium losing 2 electrons, oxygen gaining 2 electrons. So here oxidation number of calcium will be +2. Oxidation number of oxygen will be -2, because gain of electrons denoted with negative sign, loss of electrons denoted with positive sign, right? So this is a concept called valency. And there is an activity. So 3 questions are provided in this activity. We have to find out the valencies of first 20 elements. First 20 up to calcium we have to consider, right? Hydrogen valency will be +1 and -1, both will be there. Helium, being it is noble gas, 0 valency. Lithium always +1, first group element, and beryllium, alkaline earth metal, second group element, +2. Boron, -3 is possible, and even +3 is also possible. Carbon, +2 state is there, and even +4. +4 is the common valency of carbon atom. And nitrogen contains a series of valency numbers. So series of compounds are possible. That's the reason why nitrogen found a very great extent of applications in the industry. So many type of compounds are synthesized based on nitrogen because it is very essential for the livelihood even. That's the reason why, yes, nitrogen finds significant applications because various series of valency numbers are available so that it able to give the various number of compounds that able to form bonds with oxygen, halogens, hydrogen. So many wide range of applications are available for this nitrogen. Next is about oxygen. Oxygen general valency will be -2, and it able to give valency of 0 even, and +1 is also valuable with respect to fluorine. So if it able to form bond with fluorine, it will give place oxidation state also, +1, +2, -2, -1 is also valuable. You can find hydrogen peroxide -1 state is also valuable, but general electronic configuration will be -2 for oxygen. For fluorine, -1 and +1. Neon, it will be 0, obviously, being it is a noble gas. Sodium, there is no another possibility, only +1 state is possible. Magnesium will give +2 oxidation state. Aluminium, the possibility will be +3. Aluminium, whatever aluminium compounds, mostly aluminium available in the nature in the form of oxides only. So many minerals and ores are available for oxygen, and most commonly available one is a bauxite, alumina, and it's a related ore. Hydrated alumina is called bauxite. That in that also it found in +3 oxidation state. Silicon is also having various oxidation states, including -2, -4, +2, and the +4 will be there. Phosphorus, so this is a kind of another most important compound, and it also belongs to nitrogen family, and a wide range of applications are present for even for phosphorus. -3, +1, +3, +5 are the common oxidation available for this. Sulfur, atomic number will be 16. Sulfur, when you go with a dihydrogen sulfide, it will be -2. When you go with oxygen, if it is able to form bonds with oxygen, it will be in the +2 oxidation state also. +4 is available, +6 also available. SF6, if you consider sulfur hexachloride, in that it exists in the form of +6 oxidation state, maximum valency of this sulfur. Chlorine able to form -1, +1, +2, +3, +4, +5, +7 even. Right? Organ, again it is the noble gas, a completely filled octet configuration will be there, 0 oxidation state. Potassium, +1, there is no another choice, only +1 is the common oxidation state. And the calcium, it found a +2 oxidation. So these are the various oxidation states with respect to elements ranging from 1 to 20. And how does the valency vary in the period going from left to right hand side? Valency variation, you can clearly observe for alkali metals, they are commonly exhibiting +1. For alkaline earth metals, +2 will be there. And for transition metals, various oxidation states are possible. More than one oxidation state is possible. For example, if you go with manganese, +7 is the highest one. +5 is also there, +4 is also there, +2 is also there. That's the reason why more than one oxidation state, oxidation is the common term, common kind of criteria for transition metals, because transition metals are possessing various kind of oxidation state. That's the reason why they are having catalytic property. So if you go with any industrial preparation of bulk materials, bulk chemicals, so in most of the cases you can find any transition metal as a catalyst. So here in Haber's process, for the synthesis of ammonia is very essential for various purpose. So in that case, iron is the common metal working like a catalyst. In the similar manner, whatever kind of bulk material synthesis, chemical synthesis, these are the transition metals. Because of their various oxidation states, they are working like a catalyst. They are facilitate the rate of the reaction, increase the rate of the reaction in the shorter time, right? So here, that's the reason why we can't assume any kind of oxidation state to to these transition metals. +1 for alkali metals, +2 is given for alkaline earth metals, and this 13th group elements are showing +3 and followed by +4. Otherwise +4 oxidation state is also possible. You may say 0 oxidation state for these 14th elements, and -3 is given for nitrogen family elements. Oxygen family elements, common oxidation will be -2, and the halogen family being all are electronegative in nature, they are having strong tendency to gain 1 electron, so that -1, and noble gas elements having 0 oxidation state. Lanthanides, this is the most important thing. All the lanthanide elements are having the stable oxidation called +3. Exceptionally, cerium is having +4, but apart from that, remaining all elements in the lanthanide series having oxidation +3 only. In case of actinide, there is a slight variation. +3 as well as +4 is also observed. Actinides having slight variation, but lanthanide elements most commonly they are able to give +3 is the common one. +3 and +4 are the common for actinides, because that is somewhat larger penultimate shell. One more electron you can remove. So this is about the general trends with respect to valency of various elements in the modern periodic table. And how does the valency vary on going down a group? So if you go with a group, so in any group, electronic configuration of valency shell remains constant. That is the fundamental thing. Based on that only, each and every group resembles in their properties. I'm taking alkali metal as a example: lithium, sodium, potassium, rubidium, cesium, and francium. These are the elements which are present in the alkali metal, are the first group elements, where all are having tendency of ns1 as the general electronic configuration. Only one electron is available to lose. That's the reason why here common valency of all these elements are regarded as only 1. No change in the oxidation state you can observe when you are descending in a group. For first group elements, valency will be 1, second group 2, third group 3, fourth group 4. And the next fifth group, 8 minus group number can be taken. 8 minus 5, 3, 8 minus 6, 2, 8 minus 7, 1, 8 minus 8, 0. These are the general trends in the valency of given elements. By this, entire concept of valency was completed. So activity number 3, what we discussed, what are the various valencies of elements, and what are the general trends in the valency in the modern periodic table, and what will be the change in the valency if you consider any particular group. In any particular group, valency will not be changed. So by this we completed series we chosen. Hope this session will be helpful for your preparation. Thank you very much for your consistent listening. Thank you one and all.